Module 2 Mastery Assignment by Leslie Oy. Topic 1 Differentiability. Differentiability is a characteristic used to describe a function wherever a derivative exists at a certain point. We can connect this to the concept local linearity. Local linearity is essentially a concept for a function to look like it's linear if zoomed in enough. An important analogy that relates to this concept is us on Earth. While we know the Earth is round, on a much smaller scale the Earth seems flat. This behavior parallels how functions act as well. Here's an example of local linearity on a graph. Notice when you zoom in a lot, the graph will look like a linear line. Functions that are not differentiable, in other words have a derivative fail to exist, will never look linear no matter how much we zoom in. There are three main ways a derivative fails to exist. It can have sharp points, such as corners or cuffs, discontinuities, or vertical tangents. Here are some visuals that show how a derivative can fail to exist. An important theorem we get from this is, if f is differentiable at x equals a, then it is automatically continuous at x equals a. However, an important note is, the converse is not guaranteed. A continuous function is not always differentiable. However, the contrapositive is true. If f is not continuous at a, then it is not differentiable at a. Now let's look at an example. Analyze the derivative of the function cube root of x, or x to the 1/3 power, at x equals 0. When this is graphed, it seems like there is a vertical tangent at x equals 0, but let's look at it more analytically. Here we'll use the limit definition of a derivative. Our setup will be f prime 0 equals the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. This will then simplify to the limit as h approaches 0 of f of h over h, since when you plug in f of 0, you get 0, so that cancels out. And when you plug in h into the function, you get the equation to simplify to the limit as h approaches 0 of the cube root of h all over h, which simplifies to 1 over the cube root of h squared according to the exponential rules, which subtract exponents of the same base when dividing. At this point, we use direct substitution, which will make our denominator 0, meaning the slope of the tangent line is undefined, which confirms that it is a vertical tangent. Due to this, the function is not differentiable at x equals 0. Topic 2. Velocity, speed, and acceleration. Here are some important terms to know about this topic. Velocity tells us how fast an object moves, but also its direction. A positive velocity will move forward, while a negative velocity will indicate backward movement. Speed is the absolute value of velocity. It tells us the rate of motion regardless of the direction. And acceleration is the rate an object's velocity is changing, which is the derivative of the velocity. Here are equations which illustrate these three terms. Velocity is essentially the derivative of the position function. Speed is just the absolute value of the velocity function, which explains why speed is never negative. And acceleration is really the second derivative of the position function, or the derivative of velocity. Let's move to an example. A particle moves along a line so that its position function at any time is given by the function t cubed minus 12t squared plus 21t plus 18, where x is measured in feet and t is measured in seconds. First, we are to find the instantaneous velocity at any time t. Remember that the velocity is essentially the derivative of the position function. Here we are going to find the derivative with respect of t cubed minus 12t squared plus 21t plus 18. By utilizing the power rule and constant function rule when solving, velocity equals 3t squared minus 24t plus 21. Next we are to find the acceleration of the particle at any time t. Remember, acceleration is the derivative of velocity, so this is what the setup will look like, and by using power rule and constant function rule again, the acceleration will be 6t minus 24. Next, we are to find the particle when it is at rest. When an object is at rest, the velocity is 0, so all we do is set the velocity equation equal to 0 and solve for t. This then factors into 3 times t minus 1 times t minus 7, and we get the answers t equals 1 and t equals 7. Both of these answers will be in seconds, and don't forget to check for extraneous solutions. Finally, we are to describe the motion of the particles. You can graph the velocity function on your calculator, so this is easier to understand. The particle is momentarily stopping and changing directions at t equals 1 and t equals 7. At both of these points, the velocity is changing from positive to negative, or vice versa. It is also moving left on the interval 1 to 7, while also moving right on the interval 0 to 1 and any x value greater than 7.